Your twin leaves Earth at 55% the speed of light. When they return, 29 years have passed for you, but only 24 for them. And here is the strange part. Your twin calculated that only 20 years passed for you. Both of you used the same equations. Both of you got different answers. Welcome to the twin paradox. From the traveler's perspective, 9 years of your life simply do not exist. The moment they turn around, acceleration shifts their entire frame of reference, and a chunk of your timeline vanishes. That is not science fiction. That is physics. This is one of the most famous puzzles in all of physics, and today we are going to solve it together, step by step, because the universe is not playing tricks on us. This is simply how it works. Understanding the twin paradox. In our time video, you might remember Jack and Karen. One of them traveled close to the speed of light and came back, and while one aged normally, the other stayed young. When I told that story, I said, "Don't worry, I'm not going to get into the twin paradox." And a lot of you commented something like, saying you won't talk about the twin paradox while basically talking about the twin paradox, I mean, come on. But trust me, what I described back then was not a paradox at all. Compared to what we are about to discuss, it was perfectly normal. Just an expected side effect of relativity, nothing more than an illusion. So, shall we get to the real mind-bending part? I am not sure how well we will do, but let us try to understand the actual twin paradox together. Do any of you have a twin? Or maybe a friend who is the same age as you? Go ahead and sort it out between you, because we are sending one of you on a trip a little far away, about 8 light years away, to a red dwarf star called Lalande 21,185. You will board a rocket capable of reaching 55% the speed of light and make the round trip of about 8 light years. By the way, a light year is not a measure of time. It is actually a measure of distance, time multiplied by speed. In simple terms, 1 light year is about 9 trillion kilometers. So this trip will cover 72 trillion kilometers one way and the same distance back. Anyway, you sent your friend, or your twin, off to Lalande. We have no idea what they will find out there, but both of you are going to be waiting a long time to find out. You just a little longer than them. Here's what happens. When your friend returns, 29 years will have passed for you, but only 24 years for them. If you were both 20 when they left, you will be 49 and they will be 44. Now, even this part might seem strange enough, but believe me, there is no problem here. Relativity tells us something very clear. Every observer has their own coordinate system and their own clock. In other words, different observers traveling through different planes of spacetime measure time according to their own experience. There is no paradox in that. To calculate this difference, we use something called the Lorentz transformation. When we apply it, we find that our friend who traveled through space aged 24 years, and we aged 29. From our perspective, everything checks out. The real problem is with the one who made the trip. They are the one who is going to be shocked. Because relativity tells us something else as well. It says that from any observer's point of view, they are always the one standing still. So for the space traveler, they were stationary the whole time, and it was us who moved away from them. Because, according to the rules of relativity, no observer has any advantage over another. And that is exactly why the real paradox belongs to the traveler. Because even though they aged 24 years, if they use the exact same formula to calculate our age, you know what they would find? That we only aged 20 years. That we are younger than them. There you go. That is the twin paradox. How is that even possible? Now, if your brain is not scrambled yet, let us push a little further. Let us think about what a paradox really is. In situations like this, it feels as if something is wrong with the universe, and we just cannot figure it out. So let us define it first. A paradox is when statements that appear to be true lead to a contradiction, or produce a result that goes against our intuition. A contradiction. But in our case, the contradiction is not in the universe. It is in us. We might have made an error in one of two ways. First, we might have drawn a conclusion we should not have. In other words, one of the rules we relied on might not actually be a rule. The rules of relativity I just mentioned can actually help us here. Every observer has their own coordinates and their own clock. Every observer considers themselves to be stationary. No problems there. The real issue is with this rule. No observer has any privilege over another. Here is what that means. When the rocket accelerates, your friend feels a force pushing them toward the back of the rocket. That force is essentially gravity. Remember, acceleration and gravity are the same thing. And that is precisely the effect that breaks the symmetry between your friend's clock and yours. Because the symmetry is broken, your clocks tick at different rates. In any comparison where one observer accelerates, you simply cannot claim symmetry. So, the real issue is this. Our clocks were never the same to begin with. We never shared the same time. As we said, everyone measures their own clock. Time flows differently for everyone. And this does not only apply to time. Many other measurements, like distance and length, are also different. When one of the observers is moving very fast, other measurements become inconsistent too. That is all there is to it. So the point is not about who is right and who is wrong. It is not about whose calculation is correct. This journey simply makes you more relative, more, well, relativistic. But here, we need to shift our perspective a little. Instead of calculations and formulas, we need to look at spacetime as a diagram. All right, when we put all of this together, how do we solve the twin paradox? Like this. In this diagram, the vertical line represents time, and the horizontal line represents distance. For the one who stays on Earth, distance does not change. It stays the same. Since the Earth observer remains in place without accelerating, the space traveler moves away from their reference point. Then they turn around and come back. Their paths diverge and eventually meet again. For the one on Earth, 29 years passed. For the traveler, 24 years. But we need to break the journey into segments. For the traveler, time flows one way until the turnaround point, and differently after that. From their perspective, 24 years truly did pass. But the solution to the entire paradox is right there in front of us, in this diagram. The one in the spaceship thought we should be younger than them, and they were not entirely wrong, because from their perspective, 9 years of our life simply do not exist. When they turn around, the acceleration shifts them into an entirely different reference frame. Their perception of time makes a jump. And that jump is exactly what explains the age difference. Because the acceleration changes, the perception of time that had been symmetric up to that point shifts, and gaps appear in the experience of time at a distant point in the universe. In summary, during your friend's round trip, 29 years passed for you, and you would calculate that 24 years passed for them. They would calculate that only 20 years passed for you. But since the gap does not exist for them, the difference is right there in front of us. So, no matter how surprised the traveler is when they return, they will be younger. While they were on their way back, we were living entire years here that they know nothing about. But you know what? We can make things even more complicated if we want. What if we agreed with our traveling friend that every year I would send them a signal, and every time they receive it, they would send one back? This signal would travel at the speed of light, and as we know, the speed of light is constant regardless of anything else. So, what would happen? No matter how constant the speed of light is, when we look at the diagram, the light follows a path at a specific angle, so it takes several years to reach them. During the outbound journey, our messages take a very long time to arrive. But on the return trip, we can communicate much more frequently. So this confirms everything we have been saying. There is no paradox. The universe is not playing tricks on us. This is simply how the universe works. By the way, this phenomenon has been confirmed countless times through experiments like the Hoffele and Keating experiment. At the foundation of all of this lies what we call time dilation. No matter what, no matter how hard we try, I know it is not easy to wrap your head around this, but the universe itself is actually more fascinating than even the most exciting science fiction novel. Understanding it, trying to understand it, that is what makes this journey so incredibly rewarding. By the way, as we mentioned, the Lorentz transformations are used for phenomena like the time shifts we discussed. These formulas that seem meaningless to most of us are actually what physicists use to understand special relativity, time dilation, and the Doppler effect. Every one of these formulas that gets mentioned in class, solved, and tossed aside has a story behind it, and what I am trying to do is tell those stories to everyone who has learned or will learn these formulas, not just to solve and move on, but to truly understand, to learn, to feel the excitement. Only then can we really learn and really change things. I believe that with all my heart. And as always, until we meet again, I am so glad you are here. Sending love.